For problem 1, we're going to use the function f of x equals 3x squared minus 7x. And problem part A says determine the linearization of f at x equals 2. So the linearization general formula is L of x equals f of a plus f prime of a times x minus a. So I need to figure out what f of a is, f prime of a, and a. So the x minus 2 is telling me that a is 2. To get f of a, I'm going to plug 2 into my expression. So 3 times 2 squared minus 7 times 2, and I get negative 2. To find f prime of a, I need to calculate f prime of x first. So f prime of x is 6x minus 7. Now I'm going to plug 2 into my function. 6 times 2 minus 7 is 5. So to write the linearization of this function at 2, L of x equals f of a, which is negative 2, plus f prime of a, which is 5, times x minus 2. Part B wants us to determine the differential of f at x equals 2. So the differential is written as df f prime of x dx. So if I fill this in, we already know the derivative from part A. So the general form for any value x is going to be the derivative function, which was 6x minus 7 dx. So at x minus 2, all we know is the x value. It didn't give us a dx value. And so dx would be something like if they said, well, what is the differential of function f from x equals 2 to x equals 2.1? So then 2.1 minus 2 would be 0.1. That's how far apart are the x values. So now we can just do the general form of it. So if I plug in 2 into this function, which we did in part A, we know that f prime of 2 is 5 dx. So now all I had to do with this form is I can come back and say, all right, well, what's the change in f when we're 0.1 away? So if I plugged in 0.1, I'd get 0.5. Right? What's the change in f if I'm 0.5 away? If I plug in 0.5, then I would get 0.25. So this is the general form of the differential, and we could test different values of x that are different distances away from the x value on our y scale, or on our x scale, excuse me.